So yeah, next class we might go over test 2 if people look at it with me. So we're on to chapter 4 now, which is on what? Polynomials, right? So what's polynomial? What's that mean, polynomial? So a polynomial is poly means many, and nomial roughly means terms. So this is an expression with many terms, but it's a little bit more, we can be more specific. And polynomial functions. So what's a polynomial function? Well, a polynomial function is a function whose formula is given by a polynomial. Okay, so what's a polynomial function? Something like this. If you can write f of x is equal to something like a sub n, x to the n, plus a n minus 1, x to the n minus 1, plus plus a2x squared, plus a1x, plus a0, where the coefficients so here an minus 1, a2 and a1 and a0, these are all elements of the real number system. So, you know, this fancy math thing I just wrote on the board, I could erase, and instead of saying that, I could say are real numbers. Right. So this is a polynomial function, has a formula like this for some choice of coefficients. And a little bit more, what can we say? If a sub n is not equal to 0, then the degree of f of x is equal to n, all right? And this a sub n has a name. It's called the leading coefficient. The leading coefficient of a polynomial tells us a lot about it. So just some examples. F of x equal to 3 minus x squared plus 2x. All right. Example 2. G of x equal to the square root of x plus x plus 3. Example 3. H of x equal to x to the 13th plus x plus minus 7. All right, now, so here's the question. In my first 3 examples, are these polynomials? And if it is a polynomial, what's its degree? So what do you think? Example 1, is it a polynomial? I say no. Well, remember, one of the things we have to keep in mind is we can reorder the terms, right? Like this is equal to minus x squared plus 2x plus 3. We could do that. Then it has the same like pattern. And now you can see the leading coefficient here is from the x squared, right? So like you could say, well, a2 is minus 1, right? a1 is 2. a0 is 3. If you want to look at this guy right here, these are the coefficients. If I use you know, A0, A1, and A2 to describe the coefficients. The leading coefficient here is -1, so what's the degree? The degree of this guy is what? Did you say what the degree was already? No. So the degree is the highest power that appears in the expression, basically. It's just that. X squared gives you that the degree is 2. So 2. Because the leading coefficient here is this a sub 2, which is -1. Now, example 2, see, this is not a polynomial. See this right here? Not of form x to the n for some, count number or 0. So that means, okay, so game over, not a polynomial. Now, it's still it's a function. We could, do stuff with its formula. Hey, you're going to take the test? Yes, sir. Okay. I'll take you to the other room. Is it Micaiah or? Okay. Let's come over here to the other room and I'll get you started on it. Now take your time, but once you're done, you can come and join us, okay? Oh, thanks. Perfect. All right, I'm back. So yeah, the second one is not a polynomial because of that pesky square root function. Now, I mean, it's not something we couldn't deal with. You could do things like evaluate that formula. You could try plugging numbers into it, see what happens. Like, what would g of 1 be equal to for that one, for example? If you wanted to, you could calculate g of 1 is square root of 1 plus 1 plus 3, right? So 1 plus 1 plus, so g of 1 would be 5. Okay, but just for the sake of language, that's outside the scope of chapter 4. Okay, first things first. Now, example 3, this is a polynomial, right? Because it's a sum of power functions. By the way, this kind of function we call a power function because it's formed by x to a power. And now, I mean, specifically, it has to be whole number power functions, right? And that's all that's here, right? X to the 13th, x to the 1. Technically, this is 7 times x to the 0, if you like. Anyway, so it's polynomial. What's the degree of h of x? Would be 13. All right, great. Very good. So that's the first things first is what is a polynomial? What's its degree? Once we got that down, then we can go on to the next order of business, which is how to add and subtract polynomials, right? By the way, example 1 is our first example of a quadratic polynomial, I suppose, in this chapter. Example 4, suppose we had f of x is x squared plus x to the 4th plus x to the 6th. And g of x is 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the 4th. All right, what would f of x plus g of x be equal to? So what you do is just write it out, basically. There's my f of x. Here's my g of x. So calling it f of x and g of x is what? That's just like a convenient shorthand that saves us some writing, yeah? just a label for it. So I haven't really done much except just write them out again. Then how do you add polynomials? Well, what you got to do is like terms, right? So we look for like terms. And what I do is I either go from lowest degree to highest degree or vice versa. So which way do you want to do? Top down or bottom up? Bottom up. Okay, so are there any constants? 1. So I write that here. Is there any linear term? Is there any degree 1 term? 2x, right? And that's the only one, right? Is there any degree 2 term? There's 1 here, right? 1 there. So I got 1 plus 3, 4x squared. Very good. And how about next? Is there any degree 3 term? Yeah, just the 1 over here. So I do plus 4x cubed. Is there any degree 4 term? I guess just this one here, right? Oh, over there too? Cool. So that's 1 plus 6x to the 4th. Is there any degree 5 term? No. So what's the so by the way, like you don't have to write this, but you could write this. Now you don't have to write that. I'm just saying like technically that's there, okay? And then how about x to the 6th? We just got, plus x to the 6th. Yeah, now we don't usually write the 0x to the 5th, okay? But there you go, that's it. That's it. That's it, that's how we add. Now how about this? If I said f of x plus g of x is equal to, so I'm going to add on a problem now. Here's an add-on. Is equal to, a plus bx plus cx squared plus dx cubed plus ex to the 4th plus fx to the 5th plus gx to the 6th, right? I say, suppose f of x plus g of x is equal to a plus bx plus cx squared plus dx cubed plus ex to the 4th plus fx to the 5th, and like that, right? Then my question to you is, what are the values of a, b, c, d, e, f, g? So here's the theorem. If you have 2 polynomials, all right, and they're equal, the only way 2 polynomials can be equal is if their coefficients match, degree by degree. So equating coefficients, all right, equating coefficients is what this is called. It gives me, first of all, 1 is equal to a. 2 is b. 4, wait a minute. Oh yeah, sorry. 4 is c. There's another 4. So 4 is d, right? Oh, you said 6 is e? You're jumping ahead, weren't you? Let's see here, 6 is e, yeah. Gotcha. And then this one's kind of tricky. 0 is f. And 1 is g, right? So the reason I was mentioning that plus 0x to the 5th is that's kind of an important idea, because there are places where we'll need to be able to identify coefficients of polynomials. It's an important skill. So there's that. So thought I'd mix up this adding example with a comment about equating coefficients, because I personally get bored adding polynomials. It's just too easy, right? Like, it's kind of like easy's good, right? Now, what if you wanted to subtract the polynomials? What would it look like? What would f of x minus g of x look like? I'll let you catch up with my scribbling. Yeah, what if we take f of x minus g of x? What would that look like? So if I can erase everything I just did, right? I can just put a minus here instead. Same idea, basically. I just have to again, we'll go bottom up. So no constant term here, -1, right? And then, let's see here. So I guess maybe I should write this out. You can look at this as x squared plus x to the 4th plus x to the 6th. This is an important idea. When we have a minus, it goes through to all of them. So it's -1, -2x, -3x squared, -4x cubed, -5x to the 4th, right? That minus distributes to all of them. So what we got is we've got -1, -2x. Now, let's see here, x squared, I've got 1 here, and I've got -3 there. So I get, yeah, exactly, -2x squared. And let's see here, -4x cubed. And let's see here, I've got this one, yeah, -4x to the 4th. And what's next? I'll be lazy. Just plus x to the 6th, right? So, and there you go. That's it.
Okay, so when we're subtracting it, it's on that side. It's on the left side, and we're not subtracting from the right side. You do not make it negative. Right?
When I don't make what negative?
Okay, so we just had x to the 6th.
Yeah.
On the left side of the problem.
Mm-hmm.
Since we didn't subtract against nothing on the right side, it's not going to be.
Oh, right. Yeah, just x to the 6th minus 0x to the 6th on the other side, right? There's we're not subtracting. There's no like term to mess that up. Yeah. Let me show you another example here. I'll make this one a little bit lower order. Example 5. If we did, let's see here, x squared plus 3x minus 2, right, minus 3 minus 2x, how would that work? So this one, I don't have any f of x and g of x, right? I just gave you directly the expressions to work on. So let's see here. What I would do is I'll write it out. So this is x squared. So I'm just copying it down again, 3x minus 2, yeah? And this gives me minus 3. Minus times minus gives me plus. So plus 2x. And this time I'm going to go top down because it's just it's tops at the start already. So why don't I just go with, this is x squared. Now I've got plus 3, plus 2. So I get plus 5x, yeah? Minus 3 minus 2 is minus 5. So there you go. So we had to, the key ideas here are, yes, combine like terms, and be careful to distribute minuses. All right?
Doesn't matter, I worked it out from bottom to top.
No, this is totally,
I mean, I got the same answer.
yeah, no, exactly. This is equal to minus 5 plus 5x plus x squared. That is indeed the same answer. Totally agree. Let me mix it up a bit here. Of course, we can add and subtract polynomials, right? But we can also do multiplication. Hey, you done? So we're doing polynomials at the moment. What's that? Oh, this is boring? You should go back to the test. This is boring, I've been told. Ah, good. Well, we haven't got, no one struggles with this part. I don't think anybody struggles with this part unless they're confronted with a problem where the math professor manages to give you instructions that use words that you don't know. You know, I give you, here's polynomial, I say, find the difference of the polynomials. Now, there's a chance that there's students who didn't know the difference is the same as saying take the one and subtract it from the other, right? So using that word difference could keep a certain subset of students from knowing how to do the problem. So like short of that kind of, verbal jujitsu. Probably students are going to get these ones, but I mean, they still make mistakes, like, because we all do, you know, fall a man. So example 6. Here's another one. We get something like 3 times x squared plus 2x minus 7 plus 4 times 13 minus x cubed. All right, so I'm going to do one of these deals here, if you don't mind. So when I face something like this, what I want to do is I want to distribute the multiplication first. Like, so this is going to give me 3x squared. 3 times 2 is 6. 3 times 7, 21, but I got a minus, so minus 21, right? 4 times 13 is 52. Wait a minute, is it? Yeah, 52. Minus 4x cubed. So what do we got? So I was talking about Stuart. What we want to do is we want to collect like terms, and then we got to make a choice. Either write it like highest degree to lowest degree, or lowest degree to highest degree. Just that's a check on us, because if you do that, you shouldn't miss a degree as you're kind of checking off 0, 1, 2, 3, 4, whatever. As you go order by order, you should find like terms, right? If you don't do that kind of systematic sweep through the degrees, you might miss collecting like things, yeah? I mean, okay, so is there any other x? Well, I'll start with the constant. There's, what, 52 minus 21 is what? Okay, so we got 31, right, from these two, plus 6x, plus 6x, plus 3x squared, minus 4x cubed. There you go. So the other thing I was telling Stuart about was, another thing we got to be able to do is to identify coefficients, right? So if I told you this was equal to like ax cubed plus bx squared plus cx plus d, you ought to be able to tell me what a, b, c, and d are. What are they? Mm-hmm. 31. So you don't need B. Why are you in this class? Yeah, man. You're going to lunch with a friend in the last class or something. I mean, some kind of. I'm not thoroughly convinced you need to be here, but please stay here. I like people passing my class. It's good. But yeah, that's it. I tried to trick you. I tried to trick you by putting them cubed down to the first power, whereas these are the first up to the cube. But you do highest to lowest. But you saw right through my subterfuge. I could not get you with it. All right, good. All right. Okay, so we're agreed that adding and multiplying by number, pretty easy, right? Okay. So let's do something harder. Let's multiply. Multiplication. Now the key property is just this. A times b plus c is ab plus ac, right? This is the so-called distributive property. All right, this is the distributive property. This is how addition and multiplication work together, right? So what example was I on? Oh, thank you. All right, so here we go. Suppose you've got x plus 3 times x squared minus 10. So we want to multiply, right? So we think of, what I do is I think of this as a, And I think of this as my b, and this is my c. So I've got x plus 3 times x squared plus x plus 3 times minus 10. And then, by the way, there's two different distributive properties, right? There's the one I wrote, but there's also the other way. Like a plus b times c is ac plus bc. That's also a distributive property, right? So I use the other distributive property to work these out, right? This is x times x squared plus 3x squared plus x times minus 10 plus 3 times minus 10. Now, do I usually write what I just wrote? Almost never. Almost never. Because what I do is I pre-process those things in my head as I'm doing it, you know? I think through this and I go, well, x times x squared is x cubed, right? And that's, well, 3x squared is 3x squared. This red chalk is too dim today. That's minus 10x. And that's minus 30, right? So x cubed plus 3x squared minus 10x plus 30. Right? Minus 30, right? There it is. I would point out there's some counting we should do here. So we talked about the term polynomial means many terms, right? Binomial, what's that mean? It means two terms, right? Two terms added together, binomial. So what are we looking at? We've got a binomial times a binomial, right? Two terms times two terms. How many terms do you get then when you multiply them out? You get 2 times 2, you get 4 terms. See that? We got 1, 2, 3, 4 terms. You could call it a four-nomial, but no one says that. Now, the other thing we talked about before, while you were in your test, was degree. What's the degree of our answer here? What's the degree of this? If I call this thing, give it a name, Pac-Man of x. Nom, nom, nom. What's the degree of Pac-Man of x? 3. Right? So the degree is the highest order which appears. Okay. Example 8. Suppose we have 3x plus 2 times 2x minus 1. So the way I would think about that is it's 3x times 2x minus 1 plus 2 times 2x minus 1. That's the distributive property. And then what's that give me? 3 times 2 is 6, x times x, x squared, so I get 6x squared minus 3x plus 2 times 2, which is 4, 4x minus 2. So again, a binomial times a binomial gave me a four-nomial. But this is only a four-nomial because we haven't done what, Stuart?
Yeah, I was ahead, I'm sorry.
Go ahead. Okay, wait. Yeah, you were doing it your own way. That's good. It's good. You have, like my children, you have your own path. You will not take my advice. I understand. I'm trying to preach the gospel of distributive property, because distributive property is good news. It will solve your problems if you let it. But maybe you're foiling. First out or enter last? Yeah, you can do that.
That's how I've always been taught, so it's just easier for me. I can do it in my head.
Okay, Mr. Foil. I can rain on your parade.
You gonna make it where I can't do that?
I'm gonna make it so you can't foil. That's right. It's not hard. Suppose you got like, x plus 1 times x cubed plus 3x squared plus 7. FOIL.
I can still fold.
You can?
Well, how I do it, I don't really like to do first order anyway.
Oh.
I go from my x and then I times it all by x by them all. I do it without writing it out. You're writing it out and doing it basically the same thing.
Oh, okay, so what you're telling me is in your head, you think this times that, this times that, this times that, and then it's this times that, this times that, this times that. And that's what you write out.
You write it out, I can do it right here.
Oh, that's fine. Me writing it out is a transitory step. Left to my own devices, I don't write this stuff out. I just do it, you know. But for the sake of, yeah. Well, a couple things. One is partial credit, and the other is just in case you didn't have that idea, you wouldn't be up a creek, yeah. So we got what, x to the 4th plus 3x cubed plus 7x. All right, now we got to fix example 8 and example 9. Neither one of them are done, right? We're not done until we've collected like terms. Because that's just like, you know, I don't know, it's like taking your trash can back to the house after the trash has been collected or something. It's just good manners, you know. X to the 4th is the highest. X cubed, I got this guy. What's that? Plus 4x cubed. I'll buy it. How many x's do I got? Just this one, right? Oh, where's my x? I'm sorry, I've lost my squared. This is x squared, right? Plus 3x squared. Sorry, I was jumping ahead. And then plus what? Plus 7x plus 7. And there you have it. And this one, the 4 and the 3 combine, right? So we get 6x squared plus x minus 2. So there's that. So I think you guys can multiply, right? Not a problem, I think. So like all of the exercises in section 4.1 are like collect like terms, you know, pretty much. And there is a smattering of problems where they ask us, well, evaluate the polynomial. I guess we could do one of those. Example 10. If I tell you f of x is x squared minus 3x plus 2, I can say, what's f of 0? What's f of 1? What's f of 2? So how do we figure out f of 0? We plug 0 into the formula, right? So we get 0 squared minus 3 times 0 plus 2, otherwise known as 2, right? And how about f of 1? We get 1 squared, right? What's that? That's 1 minus 3 plus 2. That's 3 minus 3, right? That's 0. How about 2? F of 2. There you've got 2 squared, right? Minus 3 times 2 plus 2. So what's that? That's 4 minus 6 plus 2. So that's, alternatively, that's 6 minus 6, right? If I put the last and the first together, I got 6, and I got a minus 6 in the middle. 0, right? So that actually would be very helpful if we were going to graph this, right? Because what does that tell you? Graphically, this tells us that the y-intercept is at 2, right? and that at 1 it's going through 0, and at 2 it's going through 0. And if you knew a little bit more about this, you'd understand that this is a quadratic polynomial, so it looks like this. There you go. That's the graph of y equals x squared minus 3x plus 2. Now, that is not in section 4.1, so this is just bonus example. Something I think we get back to in like chapter 7 in your text, okay? But there's something we do much earlier, which is factoring. What's factoring? You're like, oh, see, multiplication, we can all multiply, right? Multiplying is not hard. I mean, multiplying is harder than adding and subtracting for sure, but it's straightforward, right? You just do that thing you said, like think about all the possibilities, multiply them, add them together. You got it, right? Factoring, though, factoring is a little bit harder. See, factoring is the opposite of multiplying. Sometimes I say factoring is unmultiplying. So we'll have to spend a lot more time on factoring. All right, I'm just going to start factoring today by means of example 10, actually. I mean, I'll do a couple of easy examples of factoring before we're done today. I think we have time. Maybe. Yeah, I think we do. So how about this one? X squared minus 3x plus 2. So the idea of factoring is, can you write the polynomial you're given as a product of two polynomials of lesser degree? So what I do, when I got x squared here, I'm going to put an x here, and I'm going to put an x here, because that's what has to happen in order, if you're going to multiply these two out to get back to x squared, you got to put an x here and here. And then I think about 2. How can I get a 2? I can get 2 as either 2 times 1, right? Yeah, negative 2, negative 1. And so it's got to be one of these two choices here pretty much, right? So you could try plus 1 and plus 2. But that doesn't work, because what? Yeah, because when you multiply this back out, you get 3, not minus 3, right? So we're forced to the other choice, if we only think about whole numbers. And we do, at least for a while here. Pretty much always in this course. There are some fractions that appear here and there, right? But you're like, they don't have to. You can excommunicate them from this course, right? So there it is, x minus 1 times x minus 2. That factored, right? It's not an accident that this is equal to 0 when what? X is equal to 1 or x is equal to 2. That's what this thing showed us. That's not an accident. That's what's called the factor theorem. Factor theorem says that, let me just write it out. I can never say this too many times. Factor theorem. X minus c factor of polynomial f of x, the same as saying f of c is equal to 0. If you've got x minus c as a factor, that means when you plug in c, you get 0. On the other hand, what's perhaps a little bit more exciting is if you plug in c and get 0, that forces x minus c to be a factor. So that also kind of motivates why we care about factoring, because if we can factor the polynomial, we can figure out how to make it 0, right? We just put in the opposite of the number appearing in the factor. You know? So for example, if I had, x plus 10 times x minus 13, and I wanted to solve that was equal to 0, you know what to do. You make, so the solutions are what? X equals to minus 10, or x equals to 13, right? So factoring is interesting because it allows us to solve problems, right? But factoring and solving are two logically separate things, right? Solving an equation is looking for a number that when you plug it in works. Factoring an expression, the answer is still an expression. So like, here's one. You know, we could have x squared plus 10x plus 9. Factor this. So you guys tell me what to do here. I got x. I got x. How's that going to factor? Nine and 1. So which one? Plus 1 or plus 9? It don't matter is a good answer. It don't matter. That was a trap. It does not make any difference. There's a symmetry there. You could go either way. Yeah, and then so we get, when we multiply it out, we get x plus 9x, which is 10x. Final example for today, a little bit different. Suppose you had, you know, 10x cubed plus 5x squared plus 20. Oh, no plus 20. Just like that. And you want to factor this. See, this one, what I would do is I'd be like, well, I can pull an x squared, right? I can rewrite this as x squared times 10x plus 5, right? Do you see that? So if we multiply this back out, x squared times x gives me x cubed, and that gives me 5x squared. I've been told that you didn't miss much. Today was, and I quote, boring. So, but I will post it on the YouTube, so you can see all of the exciting things you missed. Anyway, so can we do better? People are always telling other people, do better, do better. I hate when people say that. One of my most hated sayings, do better. How about you shut up? I could do what? I could pull out a 5, right? So this would be what? 5x squared times 2x plus 1. You could do that, right? So we're just starting to look at factoring. So earlier today we talked about how to collect like terms, how to add polynomials, how to multiply polynomials, and now we're just starting into factoring. We'll be doing much more factoring this week, right? So anyway, that's it for today, actually.